So today we're going to be doing area bounded by polar curves. And it's a little different than the last area with polar curves because that was like the region of the whole polar curve or maybe a part of it. And this one is between two curves, okay? Sometimes they look more like the second one twice, and other times it's just like a simple R equals equation. It doesn't have to be R in terms of theta. It can be like R equals 1 as you see there. Hopefully you're jotting this down as I'm talking about it. And let's get to the idea, okay? So in this particular one, it is a limacin. R equals 1 minus the cosine of theta. And it is a cardioid one because A is 1 and B, even though there's a minus sign in between, whether it's minus or plus, you just look at the number before the cosine of theta or the sine of theta. And in this case is 1. 1 over 1 is 1, so I think of, there's 1 for your heart, and it's like heart-shaped or cardioid. So all makes sense. Now, R equals 1 is a circle. You're going around the polar coordinate system, and it's going to create a circle with R being 1. There are other forms where R could be in terms of theta, such that it does give you a circle. As long as this value here is just 1, if that turns in, you can have like any number there. As long as there's no plus or minus, it won't be a limacin. If there's a number there, and it's 2, 3, 4, 5, 6, 7, then you're going to get a rose curve. So while you copy this down, let me just give you an idea of what like a rose curve looks like. I feel like I've mentioned it before, but we never really had a chance to kind of explore a shape of one. So if let's say you have R is equal to 2 cosine of, we don't want to say theta, but like, let's say 3 theta. Okay, that's going to be a rose curve with 3 petals. And you can have like 4 petals, and if it's 4 petals, it would be 2 theta. Okay, and you just multiply the n value when it's even by 2, and that's why you would get 4. So if you play around with your graphing calculator, you could kind of come up with interesting ones. So if you want an 8 petal, a flower looking curve here, then you would want to put something in like 2 cosine of 4 theta. Okay, 8's my favorite number, so if I wanted an 8 petal one, that's what I would be putting in, and I wouldn't want to be sketching that. I'll show you why. So let me get back to the 3. So when you sketch it out, oops, let me erase this. Okay, what happens is that you kind of start out here, and you go through the pole, and you come around, back to the pole again, because you have negative R values, and then it comes back to 0. I didn't do such a good job on that second petal, so I messed it up a little bit, but that's how it's creating those 3 leaves. So I point this out to you because sometimes you're asked for just like 1 petal for an inner curve, and kind of extending from the last lesson. So you can just use from 0 to pi over 2 and multiply it by 2 because you would get the whole petal. If they wanted all 3 petals, you would just, because it's all symmetric, multiply it by 6. So that way you can just use like 1 interval that's like easiest for you to work with. Now, the reason I also did this too is that maybe it's not, okay, the region inside our petals, but maybe it's something that is a shaded region outside. So I created this circle that's going around, okay? And this is a radius of 2. So like you're given like r is equal to 2 here. And so maybe they want to know like the shaded region. This is not the right color I wanted. Shaded region is now in red. So you would do like the circle, okay, area. So now you would get almost all of that red region, but you'd also get that rose. So you do the area of the circle, and you subtract the area of that rose curve, okay? And that's essentially what you can do even for the example that I'm showing you now, okay? But I'm going to show you a different way. So if you do get two equations that are both r in terms of theta, you can still find the area between your polar curves. Okay, so as you can see here, okay, you know the area of a region, okay, for one function, okay, or I should say for one polar curve, what you would do is subtract another one from it, okay? So you need to know like what's the outside, like what's the inside, that sort of thing, or like what's out, you know, towards the side, or what's towards like the left and the right, etc. You just basically subtracting the two, okay? So you would use this equation here. And once again, you can take out the 1/2. So you have 1/2 the integral of r squared, or r sub 2 squared minus r sub 1 squared with respect to theta. And these are theta values. I'm going to list it as theta sub 1 and theta sub 2. Okay? So let's take a look at what we're working at here. All right. The area of the region, okay, that lies inside the circle r equals 1 and outside the cardioid of r equals 1 minus the cosine of theta. Okay. There is an exact value for this one, but even the textbook gave an approximate value. Okay, so they also told me the exact value here is going to be 2 minus pi over 4. Okay, so you could probably use some sort of trig identity, or even use substitution or integration by parts in order to solve this by hand. But we're going to see about using the graphing calculator. Now, one of the reasons to use the graphing calculator for this problem is to also see where our graphs lie, instead of trying to sketch this completely by hand. Okay, so I hope that I had said it in the previous video. If I didn't, the mode in your calculator is not function, it's not parametric. You're going to move it over to POL for polar. And you can put in r equations that are in terms of theta, or you can just put it like r is equal to 1. So this is the graph that you would get. Again, I use Zoom 4 after I used like a Zoom 6, and I saw it was too smushed in there or something. It wasn't clear. All right. Okay, so the region that lies inside the circle but outside the cardioid. So that would be this region here that I'm trying to shade in red. Okay, it's inside the circle, but it's not in the lemmasin. It's outside that cardioid lemmasin that I was talking about. So in order to do this problem, we have to identify that the outer curve is the circle, okay, and the inner curve is our cardioid. So r sub 2 is going to be the first equation that's listed here, r equals 1, and r sub 1 is the second equation that they give us. So if I plug that into our formula, Okay, we can take out the 1/2, and we're going to write the integral of 1 squared, which I know is 1, minus a 1 minus cosine of theta squared. Okay, this is all our expression before we integrate that with respect to theta. And now we just need our theta values where they intersect. Okay. Okay, so this is where we may see it, but it may be a little bit tricky. So we see like where these intersect, as well as you can see it's like the top part of where our region starts, and bottom part, where it starts or ends. That's just kind of the question. So we can see that this is pi over 2. Okay, and if we go around this way to get to this angle, which is how it's being graphed, it's 3 pi over 2 down here. Okay, well, that's what I'm saying is a little bit of the problem, because the region that we're shading in is between quadrants 4 and 1. Okay, here's quadrant 1. And that's a measure of pi over 2. And this is quadrant 4. Okay, where our shaded area is, it's not going into quadrant 2 or quadrant 3. It's down this way. And that's going to be a different way to write our angle. Our angle can be written as negative pi over 2. Now, if you don't know it in radians and you know it as degrees, okay, you would have to convert negative 90 degrees. It becomes negative pi over 2. So that's what we want to actually use for our lower bounds. And the pi over 2 is definitely used, but it's going to be for our upper bound. Okay? And then you can plug it into your graphing calculator. So if you plug this into your graphing calculator, for this part right here, let me get a different color, you get 2.429203673. Don't forget to multiply it by 1/2, or you can just keep that 1/2 inside the integral. That way you can put like the whole thing in. You get approximately 1.215. Okay? And I'm saying that the exact answer would be 2 minus pi over 4. I would not worry about that. I would, however, worry about making sure you understand what your limits of integration are. Now, the other thing I just want to say before I go is that since we used the formula here, we ended up doing it for any sort of curves. Okay, whether it's r is equal to 1 and let's say r is equal to 2, or r is in terms of theta and there's another one with r in terms of theta, this will work. Okay, the only difference is that if you feel like, oh, I know the area of the circle, I can use that and just subtract the area here, go right ahead. It's going to work out to be the same thing. Okay. So if you were doing that, like you were a step ahead before I did this problem, and that's how you went about it, it should work out exactly the same way, and both you and I got 1.215. All right, otherwise, like I said, this works, so it's something you can definitely use, and you should be good to go. So good luck. Let me know if you have any questions, and we're going to practice.